Another theme in your early career was first-order hyperbolic systems and propagation of singularities.
Yes.
How did you get involved in that?
Well, the equations of fluid dynamics are first-order systems.
So you were drawn into this by the general interest in fluid dynamics and shock waves and
that's right.
things like that at Courant.
That's right.
You had collaborators in this area, right?
Yes, yes.
Who were you working with?
I had many students who worked in the area. I was interested in the matrix theoretical problems that came up. First-order systems or high-order single equations. It wasn't quite clear if they were equivalent. And it seemed I had a conjecture that for one time and two space variables, they were equivalent.
Mm-hmm.
And that turned out was proved 30, 40 years later to be true. But if you have more space variables, first-order systems are more special. But they were always of interest to me.
Mm-hmm.
I loved matrices.
And some of this work was related to what became eventually the theory of Fourier integral operators, I guess.
That's right. The propagation of singularities employed.
How does it feel to see something that you began become such an enterprise?
Oh, I was glad that it was of more general use than just this special problem.
Yeah.
Let's talk a little bit about your work on numerical methods for hyperbolic equations. The idea of shocks and thinking about discontinuous solutions was already well established, I guess, when you were working. Is that right?
What wasn't made as clear as could have been is that we are talking about weak solutions.
Mm-hmm.
It was implicit rather than explicit.
So much of your work was about numerical schemes and their convergence.
Yes.
And were there previously work by less sophisticated mathematical people that got wrong solutions or non-convergent schemes?
I don't think so. But there is the most subtle point about shock waves is the entropy condition. And certain numerical schemes automatically give the solution that is the entropy satisfying. And in my work, I helped clarify why that is so.
Right.
I don't know of anyone getting the wrong solutions. What happened many times when computers became available and everybody started computing, then they suddenly, in solving hyperbolic equations, they suddenly found the solution blew up. They didn't know why. And that is because they violated the Courant-Friedrichs-Levy condition. They took the delta T too large.
Right.
And they didn't know that theory.
So they knew they got garbage without knowing why. The theorem that's now known as the Lax equivalence theorem, which somehow tells you only a few things can go wrong.
Yes.
So this was really generated by looking at such phenomena.
Well, the reason I formulated it as an equivalence condition is because at Los Alamos I heard someone lecture on numerical methods, and he said, if you use an unstable method, if you could use infinite accuracy in the arithmetic operation, it would converge, but it's the round-off errors that make it blow up. Now, I knew that was false, and that's why I formulated that stability.
Later, in areas like finite elements, there were bad schemes and good schemes, and the area was organized by mathematicians.
Yes, yes.
But in shock waves, this was the early days of computing, so there
That's
were
right.
no schemes.
That is right.
And later on, you work with Jim Glim on long-time behavior of solutions. Is that right?
Jim Glim came to Courant Institute, and I immediately recognized how brilliant he was. And he wanted to switch fields. He was in rather abstract.
He had been doing quantum field theory, I guess.
No, that was
No?
before that. He was,
Okay.
some more abstract algebra. But he wanted to get into something in analysis and more concrete. So I suggested to him shockwave problems, and he did a brilliant piece of work.
And also in this shock area, you had some very successful students. I guess the Lax-Wendroff scheme
Yes.
is recognizable in this area.